Thank you so much for inviting me. It's a pleasure to be here. I will continue talking about neutrinos in the context of core collapse supernovae, but today I will be mostly focusing on how we model neutrino transport in core collapse supernova simulations and how different choices of interactions and or transport schemes affect on nucleosynthesis yields. My outline today is to briefly remind you what the massive stars are, the evolution, theory of core collapse supernovae, and the role of neutrinos, which Shashank mostly covered yesterday. Then I will move on to different approximate transport schemes for modeling neutrino transport. And hopefully, if time allows, I will talk about some of the nucleosynthesis outcomes. When we talk about massive stars, we usually mean stars that has masses greater than 8 solar mass. These stars spend most of their lives fusing hydrogen into helium, staying stable on the main sequence. But once the hydrogen is exhausted, these stars continue fusing heavier and heavier elements from helium to carbon, neon, oxygen, etc. And at the end of the evolution stage, we have this onion shell-like structure, where at the center we have a core that mostly consists from iron group elements. This core initially is stable, but as it reaches Chandrasekhar mass limit, it collapses under its own gravity. As Shashank described yesterday, collapse stalls, bounces, forms the protoneutron star, launches the shockwave, which initially expands and moves outwards, but very soon loses its own energy and stalls at about 100 to 200 kilometers. And then the question that we are trying to understand is how successful explosion happens. What is the mechanism that revives the stalled shock? And as you have seen already yesterday, we believe that neutrinos are mainly responsible for re-energizing the shock and shock revival. Neutrinos transport energy from the protoneutron star to the outer layers. They are absorbed by the material behind the shock. They reheat this material. Plus, we have neutrino-driven convection, and all these can cause further continuation of the shock to move outwards. So we believe that neutrinos are the main ingredient into getting successful core collapse supernova explosions. So in that sense, it's crucial to properly model neutrino transport, but it's not that easy. It's quite challenging because not only we need to model neutrino transport, we need to couple it with hydrodynamics, general relativity, and nuclear physics, and that can get quite challenging and quite expensive. As we stand at the moment, approximately to give you an idea, one three-dimensional core collapse supernova simulation takes about a couple of months to be completed, about 10 million CPU hours, so it's quite expensive. What we are interested in today is to figure out how we can cheaply and efficiently, but still accurately model neutrino transports to capture all the physics that is important for explosion dynamics. And as Shashank already explained yesterday, in order to model neutrino transport, we need to solve the 7-dimensional Boltzmann equation. This is the same form as you have seen yesterday, just a little bit of twist. It takes into account the gravity effects in there. So X alpha is the 4-position, 4 momentum, P alpha is 4 momentum. We have neutrino distribution here, which depends on neutrino species and neutrino energies. And on the right-hand side of this equation here, we have all the neutrino interactions that are possible in the environments of core collapse supernovae. So let's look at the left-hand side first. We need to solve this equation for it's a species dependent. So we need to solve these equations for different species. This is already complicated. Plus, we have 3 position, 3 momentum, and time. So we are dealing with 7-dimensional physical domain. Let's say, to give you a rough order of magnitude estimate, if we want to have around 100 beams, for example, in each direction, then we are already talking about the domain that is 10 to 8 in size. So full Boltzmann transport in core collapse supernovae roughly takes 10 to 7 CPU hours per run. Now, let's make things even worse. Let's look at the right-hand side. In the right-hand side, I told you that we need to take into account all the neutrino interactions with matter, with each other. But this is not what typically is done because we can have a lot of possible interactions and it's not possible to model all of them. So what is typically done in supernova simulations is we try to take into account these first three reactions, the processes here, the beta processes, peer production and neutrino scattering with matter. In most sophisticated simulations, they try to take into account and include all the reactions here, but in some of them, they don't even include all this. And it has been shown that given what interactions you include, you can get quite different explosion dynamics and outcome. So what concerns about neutrino-neutrino interactions, Shashank talked about this a little bit, but typically from the supernova point of view, we are not able to self-consistently model neutrino-neutrino interactions within the supernova simulations. So typically simulations don't take into account this at all. Okay, so yesterday you saw how we can simplify this 7-dimensional neutrino transport problem by assuming, for example, spherical symmetry to reduce the dimensionality and try to solve the Boltzmann equation. Today, I want to show you how to not solve Boltzmann equation, how to get away without solving Boltzmann equation at all. Over the years, there has been a lot of approximate neutrino schemes, transport schemes that have been developed. I will try to show you examples of couple, and I will start from the lowest accuracy, but the cheapest neutrino transport scheme, which is called the leakage scheme. So the idea of this leakage scheme is very simple. So we have neutrinos that have different energies, different flavors. You have seen yesterday that depending what the energy of neutrinos are, the decoupling radius for them are different. They have different mu-free pulses here, and depending what neutrino mu-free pulse is or neutrino optical depth is, they can be either trapped or they can be free streaming. So in this region somewhere closer to the neutrino sphere, neutrino mu-free pulse is quite small. So we have kind of trapping regime where neutrinos are trapped. As you go farther out, you will reach the region where neutrinos are free streaming. So the leakage scheme tries to smoothly transition from the trapping regime to the free streaming regime by just assuming simply that neutrinos leak. Some part of neutrinos leak, and there is a single energy isotropic leakage assumption, and the energy loss due to this leakage can be determined by the emissivity, a local emissivity at that point, and neutrino mean optical depths. Okay, so to intuitively understand this formula, you can imagine that for very large optical depths, this term here is quite small. So if the optical depth is very large, no neutrinos can leak, so they are trapped. If optical depth is very small, then basically all the neutrinos can leak, and you have a free streaming regime. This scheme can work very accurately if we are dealing with, for example, early collapse phase or early post-bounce phase, where we have our core is highly opaque. And typically what happens is that we turn on this leakage scheme during the collapse phase, and soon after the bounce phase, we try to switch to something more advanced like moment scheme that I will discuss later. Okay, so next scheme is the moments method. Now, Again, if we start from the Boltzmann equation, instead of solving Boltzmann equation, we can consider different moments. If we integrate the distribution function in the momentum space, we get the 0th moment, which is energy density. If we multiply it by momentum, then integrate, we get the flux density. And then we can get the pressure density, the pressure tensor similarly, and you can go all the way to the higher and higher moments. And once we do that, then we will get the evolution of equations. From the Boltzmann equation, we get evolution equations for each of these order moments here. For example, here I'm showing you the energy density evolution equation and flux density evolution equation. What I want you to, this is typically where we stop, and it's called M1 scheme, which only takes into account the evolution of first 2 moments. But what I want you to pay attention here is that if we want to solve evolution equation for energy density, for example, it depends on flux. And the evolution equation for the flux depends on the pressure tensor. So each evolution equation depends on higher order moment, which means that you always have more unknowns, more unknowns than you have equations. So to solve this system of equations, you need to truncate this moments at some point, and you need to introduce the closure relation. For example, in this case, we need a closure relation which relates the pressure tensor to the energy density and flux. And in the typical moment scheme, this closure relation is some sort of analytic relation. So then we have the 2 evolution equations plus the closure relation, and we can solve this within the Korolov-Supernova simulation. So this method is nice, and this is what's typically used and done in most of the simulations. It captures both diffusion and free streaming regimes, but the problem here is that the closure relation is not uniquely defined. And there are different closure relations, and depending on what the choice for closure is, you can get different outcomes. More sophisticated scheme is the Monte Carlo neutrino Monte Carlo transport. In this case, we consider, instead of distribution function, we consider it as an assemble of neutrinos. For example, if we take a physical cell at some location, and given whatever emissivity is, let's assume that there 10 to 52 neutrinos are produced. Instead of tracking each 10 to the 52 neutrinos and considering interactions for each of them and evolution of each of them, we maybe introduce 100 Monte Carlo particles, each of which will have correspondingly 10 to 15 neutrinos in there. So that allows us to now, instead of now consider this 100 Monte Carlo particles, how they evolve. So we basically weigh this neutrino distribution into the Monte Carlo particles, and then we absorb, emit, and interact Monte Carlo particles instead of each neutrinos individually. As the particles travel, interactions are probabilistic, but the problem, it's not a problem, but once we have one Monte Carlo particle that consists of a lot of different neutrinos, we are specifying that this Monte Carlo particle is characterized with single position, single energy, and single direction. This is suitable, very suitable, and very well works very well in optically thin regions where we don't have the requirement to have a lot of neutrino particles. However, as we try to model the protoneutron star, or somewhere closer to protoneutron star in optically thick regions, their mean frequency is very small, and interactions, a lot of interactions happen. And in order to reduce the noise and have any sensible or accurate result, we will need to increase the number of Monte Carlo particles drastically. And that's quite a bit of challenge to do so, because once you increase number of Monte Carlo particles, then your simulation cost also increases. So what's often done is people try to model or use some different approximation for optically thick regions, for example, something like diffusion-based model, and then outside they try to model with Monte Carlo simulation. Okay, so next scheme that I would like to discuss is some kind of combination of the moments method and Monte Carlo approach. It's called method of characteristic Monte Carlo scheme. In this, basically, what you do is very similar to the M1 moment scheme that I described. You still solve the moments equations. However, instead of using some analytic closure, we can actually calculate and evaluate this closure using the Monte Carlo sampling. So instead of analytic closure, we do Monte Carlo. We find what is the relation between the pressure tensor as a function of energy density and flux. And this allows us to have a better and more accurate angular distribution information. So this method is most promising in core collapse supernova simulations because this method, one, can work in both diffusion and free streaming regimes, both optically thin and optically thick regions. This is not as costly as the full Monte Carlo simulation would be, because we are still solving the moments equations. It's a bit more expensive than the moments method because we still need to use Monte Carlo to find the closure relation, but it's more accurate and not too expensive to use. Okay, so to sum up these different approximate schemes, there are many more, by the way, and there are a lot of different variations, for example, for leakage or for moments. For moments, you can imagine, or for leakage, for example, you can imagine instead of having one energy, you can have a spectra of energies. Then that's some sort of advanced leakage scheme. Then for moments, you can imagine to not stop at first 2 moments, but continue until, I don't know, 3, 4, 5. The higher you go, more accurate your result will be, but then more expensive your simulation is. Then for Monte Carlo, again, one needs to somehow take into account how to model the proto-neutron star in that sense. And then the highest accuracy, but also the highest cost has the Boltzmann solver that you saw yesterday. So there are some approximations to solve, if appropriate, for example, to use a spherical Boltzmann, something like that. Okay. Now let's talk a little bit about nucleosynthesis. So we said that stars synthesize elements all the way up to iron during their evolution, stellar evolution phase. When the supernova explosion happens, all these elements that stars synthesized are released in the universe. But nucleosynthesis from core collapse supernova does not stop there. After explosion, we can still produce heavier elements beyond iron group elements. And as you can see here, so these are the icon for all the elements that can be produced or can be resolved due to supernova explosion. As you can see, beyond iron, there are a lot of elements that are still produced as a result of core collapse supernova explosion. But this is the after explosion phase. There are multiple ways to produce heavier elements beyond iron. One of them is, for example, alpha-rich freeze out. So again, neutrinos play a crucial role here because neutrinos hit the material just behind the proto-neutron star. This causes the rapid cooling and expansion of these outer layers there. So if initially your system was in nuclear statistical equilibrium, as due to this rapid cooling and expansion, nuclear statistical equilibrium is broken, and we get the excess of alpha particles there. So now we have a bunch of alpha particles that can be combined with nuclei and produce heavier nuclei like nickel or zinc. Then if the core collapse supernova ejecta is proton rich, then protons can be converted into neutrons by protons can be converted into neutrons. Now we have the neutron captures that can happen and trigger. This neutron capture triggers the creation of elements just before, just after iron here. So these elements. Then instead of proton rich, if the outflow or ejecta is neutron rich and we have high entropy, then it can trigger our process nucleosynthesis, and that can create even heavier elements like gold, platinum, uranium, etc. So these elements up to iron are mostly created by the evolution phase, while heavier elements are mostly created after the explosion happens. Now, what determines if, in order to understand which elements will be produced after supernova explosion, we need to know what kind of ejecta we had for the explosion. After the explosion, did we have proton-rich ejecta? Did we have neutron-rich ejecta? Then we need to know what the electron fraction is. We need to know what the temperatures and entropy, are, and all these are set due to the whole explosion dynamics, which is greatly affected by neutrinos and neutrino transports. So to make any sensible estimates of what nucleosynthesis yields we get from supernova, we need to be sure that we are accurately modeling neutrino transport in supernova simulations. With that, I'm going to put up my summary and say that there are different neutrino transport schemes. Some work in one region better than in another. We're still trying to take into account the neutrino-neutrino interactions, how they would affect. We're still trying to figure out how including different neutrino interactions can affect explosion dynamics and explosion ejecta. But most importantly, probably the takeaway message that I want to share today is we need to accurately transport neutrino, accurately model neutrino transports to have accurate estimates of what the explosion dynamics and nucleosynthesis yields will be from core collapse supernovae.
Thank you, Mariam. Other questions? I can maybe start with one. So you had the this collision term at the beginning of your transport equation. So when you do this moment expansion, you also get a moment expansion of this collision term. So is this part of this kind of I mean, this closure that you were talking about, is this then closure in terms of the moment expansion of this collision term, or how do I have to imagine this condition?
Yeah, so usually it's the interpolation between, we know what the diffusion regime should look like. We knew what the free streaming regime should look like. So this analytic closures that I was talking about is often just a simple interpolation of these two regimes, between these two regimes.
Oh, yeah, okay. Yeah, let's start here.
Thank you for the very nice talk. So you mentioned that we don't know so much about the effects of the neutrino-neutrino interaction. So in that case, do we actually understand if the medium is actually optically thin or thick? Like, do we have a good hold of the estimation if we don't
If you don't
like
understand.
if we don't take into account of the neutrino-neutrino interaction inside the core, do we get a good sense of if the medium is actually optically thin or not?
Now,
Yeah.
my zero-thought answer to that would be yes. You can still, based on neutrino matter interaction, you can still define optical thin and optically thick regions, and that's typically what we mean by optically. That's how we determine the optically thick or thin region. But I don't know if you want to comment anything on that.
Yes. Good that it's raining now and not later. Yes, Shashank, did you want to say? Do we have another question? One of you?
Yeah, just so I didn't quite catch, how do you do the Monte Carlo sampling? Because I can imagine you, I don't know, sample this using distribution functions normally, but then if you don't know the evolution of the distribution function, how?
So what you do is you have emissivity that, for example, tells you for particular flavor, tells you how many neutrinos can be produced within a cell locally, right? Then you weight, you introduce this weight function here and weight these neutrinos. Then you have number of Monte Carlo particles within the volume, within the particular cell. So yeah.
All right. And then one more question, if it's okay. So just to get an idea of the sensitivity, like, could you use this also to say something about neutrino interactions? Because I guess normally we cannot really measure in the lab like neutrino-neutrino scattering. So could you, using like Monte Carlo or like some mode half thing, also get information?
I don't know. I don't have an answer.
No? Okay.
Probably yes, but I could not explain how.
Yeah, I think.
John, okay, thank you for the nice talk. When you compare the different methods to compute the dynamics, there was I think that you were comparing the cost and the accuracy. I was wondering, when you say low and very high, how do they compare? Like if you do the rough global estimate compared to the exact global, the exact Boltzmann computation, are there other phenomena that can emerge? Like if you do a rough estimate, assuming I don't know, a lot of symmetries and continuous approximation, are you missing a lot of information? Are there maybe, I don't know, instabilities or something that only emerge in the Boltzmann, so that when you compare the two, they are really, really different?
Yeah, for example, when you use the moments method or the leakage, for example, you lose all your angular information whatsoever, right? Then there are some methods that can, for example, try to recover this angular information that we thought that we had lost during when we are doing calculation, for example, for the moments method, but then that's also not uniquely defined. So yeah, I mean, if you do full Boltzmann, then you or Monte Carlo, then you still can keep the angular information. You can have I don't know, you can estimate where the Euler crossings are, and etc. etc. When you do moments scheme, then you basically have no angular information whatsoever because you have integrated it. Right. So yeah, you in fact lose and sacrifice quite a bit just to gain the computational costs.
Okay, thank you. Okay, I think we have to move on. So let's thank Mariam again.